Hello, I'm Alexander Pushnitsky, your lecturer on the Real Analysis module. In this introductory video, we will go through the content and the organization of the module. Let me start with a historical perspective. From the time of Newton and until the late 19th century, analysis was exclusively about nice, smooth functions, mostly functions given by explicit formulas and functions whose graph you can easily plot. Here is an example. I've plotted the graph of the function sine of x over x. It's a lovely explicit function. You can differentiate it as many times as you want. You can expand it in Taylor series, you can integrate it, and so on. Now let's look at the right-hand side of this slide. Here we see a sample plot of a function known as the one-dimensional Brownian motion, or a Wiener process. Such functions play a key role in modern mathematics, physics, and engineering. The theory underpinning these functions governs financial markets and is important in electronic engineering, control theory, material science, and many other branches of science. Looking closely at the graph on the right-hand side, you will see that this function is continuous but not differentiable. Its graph is very jagged. Indeed, functions of this class are not differentiable at any point. If you blow up a little piece of the graph, you will see that the same jagged structure persists. A first example of such functions was constructed by Karl Weierstrass in 1872. Weierstrass himself said that he has created a monster. His function was expressed as a sum of infinite series. It took his contemporaries some time to accept the existence of such functions in the abstract mathematical world. Today, we know that such functions are as real as sine and cosine. Weierstrass's example has sent a message to mathematicians that they have to perfect their tools, their analytic tools for working with such functions. Indeed, many of the tools of the classical analysis, such as differentiation, the fundamental theorem of calculus, and so on, are simply not applicable to such functions. So mathematicians had to perfect their tools, and out of this grew real analysis, modern real analysis. Let's discuss the content of the module. The prerequisites are calculus 1 and sequences in series. The main object in the module will be a real-valued function f of a real variable. The main topics are continuity, differentiation, integration, and sequences in series of functions. For more details, look at the detailed syllabus on KEATS. If you look at this list of topics, you will suspect a strong overlap with calculus 1. Indeed, nominally, there will be some overlap in terms of notation, terminology, etc., but there will be also important differences. Here, we will focus on rigorous justification of procedures and objects that you have learned to use without too much deep theoretical analysis in calculus 1. The second difference is that here we will pay close attention to the issue of interchanging of key operations of analysis, taking limits, differentiation, and integration. For example, let's consider this formula. The limit of integrals equals the integral of the limit of functions. This formula is sometimes true and sometimes false. In this course, we will prove a theorem which gives sufficient conditions for the validity of this formula, and one of its important outcomes will be for you to learn to recognize when this formula is true and when it is false. Another important feature of this course will be the focus on examples. So let's put it this way. If I had a choice between teaching you to reproduce delicate proofs of theorems about real-valued functions and teaching you to recognize concrete situations when such theorems apply, I would choose the latter. Because of this focus on examples, exercises are of crucial importance, and exercises are key to success. Let's talk about the organization of the course. The assessment will be made of 90% exam and 10% participation mark. 10 pieces of homework, each worth 1%. First, about exam. Past exam papers are already on KEATS. When you look at these papers, or if you come across any other papers, bear in mind that the module was redesigned in 2019-20. Previously, it was called Analysis 1. So if you come across exam papers from 18, 19 or earlier, they're less relevant to us. The exact format of the exam is unknown at present for reasons everybody understands. But regardless of the format, the content of the exam is based on the list of typical questions that you can find on KEATS. Homework, so every week you will get a homework sheet. Questions typed in red correspond to these typical questions from the exam list. Then questions marked with a star are for submission to a tutor, and other questions are for discussion during the tutorial. At the end of every tutorial sheet, you will find some challenging exercises for those students who are willing to go beyond the standard syllabus. Lecture notes are already on KEATS. Currently, it's just the portion covering weeks 1, 2, and 3, but soon I will put the rest of the notes on KEATS. Recommended literature, the reading list contains 3 books, Rudin, Haggerty, and Brannan. Rudin is a wonderful classic textbook, very popular. You will have no difficulty locating an electronic copy of it. And in fact, in the second part of the course, we will follow Rudin's book quite closely. Communication, I urge you to use KEATS forum for asking questions in preference to email. If you have a question, most likely that many other students will have the same question, so they will benefit from reading my answer to this question. I will do my best to monitor the forum frequently and to answer questions as soon as I can. That's all for today. Good luck, and I will see you soon in the lectures, at least virtually.